Hey y'all, so today we're going to start our lesson on modern physics, and in your packet that you should have the first paper in there should be the models of the atom. So you're going to use that to take your notes in the first couple of slides here. Usually if I'm giving this lecture, I ask the class if anyone knows or remembers what the J.J. Thomson model was nicknamed as. And so you might know, and if you think of it, you might have said that it was the plum pudding model. And what that means is that J.J. Thomson believed that there were negative electrons. He didn't know that they were electrons, but this negative something, like raisins in a plum pudding, and the pudding being positively charged, and the raisins but being negatively charged. But he didn't know that the electrons were electrons, and he didn't know what caused the positive charge. Rutherford further developed from J.J. Thomson's model, and he discovered by the Rutherford gold foil experiment that the nucleus was a dense, very small, but dense, had a dense center, and that center was positively charged, and that somewhere, orbiting around this positive dense center were the negative electrons. So his main development and contribution to the model of the atom was this dense nucleus. Since Rutherford did not specify what was happening with the electrons, Niels Bohr further developed where these electrons could be. Even though it is incorrect in that the electrons don't follow these perfect little orbitals, the idea, the concept is correct. And we actually use Bohr's model to explain energy level changes within the atom. So I'm not going to get into what happens as electrons move energy levels because that happens later on in this lesson. But we will say that Bohr helped develop where the electrons are and discovered that there are discrete energy levels or specific energy levels in which the electron can be. In actuality, the atom looks more like a cloud, and where the electrons are orbiting in all different directions and velocities, and we can see that from this diagram of the cloud model that towards the center in this region here there's a higher density of electrons, which means that there's more probability that an electron will be towards the ground state than it is out here in the outermost shells, meaning that they're less likely or have a less probability of being in an excited state and more probability of being in a ground state. Now you should continue to take your notes in your notebooks. The second part of this lesson is quantum theory. I'm going to start by explaining that waves and particles both share the same qualities, and this duality is called the wave-particle duality of energy and matter. So what this means, very generally, is that waves can have particle-like properties. Particle-like properties would be like momentum and kinetic energy, can exert forces. So those are particle-like properties, and waves do have those type of characteristics. And particles can also have wave-like properties, like frequency and wavelength and diffraction patterns. So it's kind of interesting. We've only studied particles a particular way, and we've only studied waves a particular way, but they do share similar qualities. So waves have particle-like properties. So as I said, waves can have kinetic energy, momentum, and we have evidence of this. And this is primarily like what you need to remember. So the idea that waves have particle-like properties can be asserted by the photoelectric effect. And the photoelectric effect is an experiment in which light was shown upon a very thin foil, and as a result, when the light was hitting that material, we had electrons bounce off. So this light hit a material, and as a result, electrons bounced off or were ejected or forced off the material. So that's very similar to saying, like, in a billiard ball table, you have the cue ball hit another ball, and as a result, that ball moves. So that is definitely a particle-like property. And the fact that light, we look up at the ceiling lights right now, it's amazing that that light can actually push electrons off of atoms. It really does that by transferring energy. And that was developed by Max Planck. And particles have wave-like properties. So it's very hard to see this in our macro world, but microscopically and subatomically, when we look at really, really small particles, they actually move in a wave-like pattern. They actually vibrate. And the fact that they're vibrating, we can understand that they can have frequency and wavelength. And also, they can cause interference and diffraction patterns, which those are definitely wave-like properties and not particle-like properties. So we can say that waves have particle-like properties and particles have wave-like properties, and that is called the wave-particle duality. Here's a little bit more about the photoelectric effect. So we have light shining upon the material, and I'll just highlight that for you. So we have light shining on the material, and then as a result, the electrons that are within that material are being ejected off the material. So really what's happening is that this light is able to give the electrons enough energy in this material to really become excited and then ionized. And once they're ionized, they have enough energy to leave their atom, and as a result, we get the electrons deflecting off the material. So it's a pretty cool experiment done by Max Planck, and then mathematically developed more mathematically by Albert Einstein. And again, this is our evidence that waves, which is light here, these are our waves, that these waves have particle-like properties. So now, there's a few things that you could do. You can type in, because it's not a link in this video, but you can type in this URL and try to play with the interactive Bohr's model. But there's another one that's a little bit better, about the same type of idea, that's located on Schoology, and it's entitled Bohr Model Interactive. So if you take a moment just to pause this video, go to Schoology, check out the Bohr Model Interactive, and it's kind of cool to see how, as the electrons are given energy in the form of photons, that the electrons then have enough energy to move to a higher energy level. And if you have the electron move to a lower energy level, it emits some energy, emits it in the form of light or a photon. So kind of cool to play around with, so definitely take a minute to do that. Also, so to explain what's happening a little bit more, so we know that the electrons move in orbits around the nucleus, and in order to move from one energy level to another, it needs to either absorb or emit, gain or lose energy, kinetic energy to be more specific. And these energies are in these fixed amounts, and the fixed amounts of energy are called photons because it's light energy. So if an electron absorbs photons of energy or these packets of energy, the electron can move to a higher energy level because it has more energy in order to be there. And the electrons can move to a lower energy level. They do this actually pretty quickly. It's much easier to be at ground state. I'm going to explain that a little bit more. But when they move to a lower energy level, they emit that energy. They don't need it in order to be near ground state. So these emitted and absorbed energies, these photons or packets of energy in the form of light, they have different frequencies associated with them. For instance, a high energy would be associated with a high frequency, and that would be more towards your like blue and violet end of the light range, or even on the electromagnetic spectrum, even different forms of electromagnetic waves. So one of the really cool things that we do is we can see this with the spectroscope. So you'll see that there's a box of spectroscopes. They're little black triangle looking devices, and the box is labeled spectroscopes. Grab one, and I want you to look into it from the smaller or narrower end. There's a square opening for your eye, and then when you're looking in it, you'll see a range of wavelengths where you'll see different colors, but there's also a little tiny opening or slit. That's where you want to focus the light. You want the light to enter through the slit. So if you just take a moment to take that spectroscope and look up at the overhead lights, fill that slit totally with light, and you should see different emissions. So you'll see different colors there, and I think for Mercury there's about 11. Some of them are so close together though that they look like just one line. So to the naked eye, it might be hard to distinguish 11. But it's really cool, so take a moment to do that. You'll find the box on the shelves in the large white cabinet. Please turn to the energy level diagrams in your reference table. So here we have the energy levels for hydrogen and for mercury. Both we're going to get to look at in our lab. So you can see that the ground state here is at n equals 1, and at n equals 1, that's the lowest energy level. This is naturally where electrons will fall to as they lose energy. And you can see that the energy level is actually negative 13.6. What that means is it requires 13.6 electron volts, which is a measurement of energy, to get that electron to leave the atom. Notice that ionization is at 0 electron volts. So at from negative 13.6 to 0, it requires 13.6 electron volts. In order for an electron to move from ground state to, say, n equals 2, it's going to require the difference in energy between n equals 1 and n equals 2. So the difference in energy between 13.6 and 3.4 is just subtract them. It's 10.2 electron volts. So the electron needs 10.2 electron volts to get from n equals 1 to n equals 2. You just simply subtract the two values. Any state above the ground state is called an excited state. And obviously the last state is ionization. Now, different elements have different energy levels, and so I'm going to explain how that works as far as what you might see in your lab. So if we look at mercury, n equals 1, or associated with level A, has a different energy level or energy state than, say, level B, or associating with n equals 2. So the difference in energies between those two states of 10.38 and 5.74, that is also different. So the amount of energy that's required for the electron to move from A to B is different for mercury than it is for hydrogen moving from n equals 1 to n equals 2. So every element is different. It's really kind of cool because each element, because it's different, we call this a spectral fingerprint. Because when these electrons move from one energy level to another, they either emit or absorb that energy, as I described, and they emit it in different frequencies. Some of the frequencies are associated with the visible light spectrum, and we can see it. We can see it with the spectroscope, which is pretty awesome. So when you're looking at the overhead lights, you're actually looking at mercury, and you are seeing the portion of the electromagnetic spectrum that we can see, which is visible light. You're seeing all the visible light emissions within mercury. I think there's like 11. So anyway, pretty cool stuff. Okay, so this is where we would transition from one day to the next. So just so you know, this lesson would normally take place over the course of 3 days. So if you are ready to move on, move on. And if not, it's okay if you pick up tomorrow. But just so you know, you want to complete this lesson within 3 days' time. So today, we want to continue talking about quanta or packets of energy. You heard me mention packets of energy in the form of light, which are called photons. So we're going to talk about that a little bit more. And we also want to talk about the relationship between energy and frequency. I don't know why that word is missing, but it should be frequency. Okay? And like I said earlier, higher frequency was associated with a higher energy, and a lower frequency associated with a lower energy. So what is quantum theory? This is primarily Einstein's developments and contributions to this idea. Quantum theory really could be applied to a lot of different concepts. Applied to modern physics and subatomic particles, we're really looking at how these electrons are gaining and losing energy, and they're doing this in these small fixed amounts or discrete amounts called quantum. So the fact that these fixed amounts are always like a unit almost, like we say a unit of time is 1 second, or we say the centimeter might be like 1 unit of length. So when we talk about energy, we have the smallest amount of energy possible is this certain amount of energy, and it's called quantum. So you can't have part of the quantum. Unlike a centimeter, you can have part of a centimeter. It's kind of like you can't have part of a charge. And you can't have part of a quantum. So light quanta are called photons, photo meaning light. As I've mentioned before, energy and frequency have a direct relationship. So, and also, as I explained with the energy level diagrams, each atom would result with different colors. We'd see those because different frequencies are emitted and absorbed. When we see the colors, that's an emission spectrum. Those are the bright colored lines on a black background. And the absorption spectrum we can't see with a spectroscope. We need another device to do that. So Max Planck discovered the proportionality between energy and frequency, and he called it Planck's constant. Planck's constant is represented by this H, and it is the proportionality between energy and frequency, so energy divided by frequency. If we solve this equation for the energy of the photon, it is equal to Planck's constant times frequency. Frequency, you know, from our previous unit, frequency is equal to the speed of light divided by wavelength, lambda. Okay, so we could substitute in c over lambda for frequency in that same equation. Please take a minute to look at your reference tables and find these equations in the modern physics section. So we're going to do an example problem where we use the energy of a photon as 2.11 electron volts. I'm not saying that's associated with any energy level change. We're just giving it, any electron volt energy. And the first thing that I want to do with you guys is determine how that energy in electron volts can be converted into joules. And then we're going to use Planck's constant to determine the frequency of the photon. And then we're going to see what color that would be associated with if it were emitted as an emission spectrum. So I had explained the energy level diagrams, and the energy level diagrams use energy measured in electron volts. And a lot of times we want to convert those electron volts into joules, our typical unit of energy, because this is the unit that's used with Planck's constant. So if we look at our reference tables on the front, you can see that 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. Okay? So since that's true, we'll set up the conversion factor so that our electron volts cancel. I don't know why that's shifted, but you know it should be over there. Okay, so we have 1 electron volt on the bottom so that our units cancel. We have 1.6 times 10 to the negative 19 joules on the top, so we end up multiplying across, and as a result you should get 3.38 times 10 to the negative 19 joules. So check that out, make sure you're able to do that conversion to joules. We need to convert to joules to use Planck's constant. So again, the frequency of the photon is determined by using the energy of a photon measured in joules. And the reason why we need the energy measured in joules from our last slide is because Planck's constant utilizes joules. If you look at Planck's constant on the front of your reference table, you'll see that H is equal to 6.63 times 10 to the negative 34 joules times seconds. So to be dimensionally consistent, we have to use our energy in joules. So we're going to use the energy we just found, 3.38 times 10 to the negative 19 joules, and we're going to determine the frequency using Planck's constant from the front of the reference table. I just made another note about Planck's constant using joules. So frequency is equal to the energy divided by Planck's constant, H. Go ahead and do that calculation, press pause. And you should have gotten, we don't have our superscripts on here, you should have gotten 5.1 times 10 to the 14th hertz. Now anything, times 10 to the 14, you should know from your waves unit is going to fall in the visible light range. So now that we have this frequency, how can we determine the color associated with it? Well, if we just look at our reference table, the electromagnetic spectrum, take a look and see what that frequency corresponds with. You should find out that the color is yellow. So 5.1 times 10 to the 14 hertz, again I apologize about the superscript, corresponds to yellow light. In your Prentice Hall books, I want you to try numbers 1 through 11 on page 186. You're going to be placing the answers to your questions for this Prentice Hall assignment in the questions that follow this slide.
As explained earlier in this lesson, particles have wave-like properties and waves have particle-like properties. So it's actually pretty interesting to see what happens when a wave and a particle collide. If you have a wave colliding with a particle, as a result, you get something very, very similar to what you studied in conservation of momentum. The wave has a velocity before, and the particle may be at rest or moving also at a speed, but we'll keep it simple and say that its speed is 0. And then after the collision, the wave might slow down or change direction. So I'm showing a lower frequency and a change in direction slightly. And the particle might then move with a velocity on its own as well. And the energy is conserved in the collision. If you check out this URL, you'll see some photon-particle collisions. It's pretty cool to see how the wavelength changes, and they actually change the color in the interactive. So it's pretty cool. Check it out, definitely, and the link is also on Schoology. So we've already talked about energy levels in terms of changes in energy and frequencies associated with those emissions and absorptions. However, we didn't talk about why or how. So in order to emit light, an electron must lose a specific amount of energy. And we know that that's different for different elements because each element has a different spectral fingerprint or a different spectral energies or energy levels. So when an electron moves from one energy level to another, we know that there's an absorption or a emission of energy, but why? So you have to think back to Coulomb's law that we studied in electrostatics. If an electron is closer to the nucleus or is moving closer to the nucleus, we have to think about the force that's acting on the electron. The positive nucleus and the negative electron are electrostatically attracted to one another. So if that electron is moving towards the nucleus, it's actually easier to be near the nucleus than it is to move away from the nucleus and go against that force of attraction. So it's kind of like moving with gravity. It doesn't take any energy to move towards the earth or fall towards the earth, but it does require energy to move away from the earth. So you can think about it in that respect. So think about the force of attraction between the electron and the positive nucleus. And if we're moving towards that direction of attraction, the electron does not need as much energy in order to be in an energy level such as ground state. But if we try to move away from the nucleus, the electron needs energy in order to do that. So it requires energy to move against that force of attraction between positive and negative. So there will be an absorption of energy as electrons move away or to higher energy levels. And generally this makes sense to people because when we talk about ground state, we know that that's the lowest energy level. There's less energy there. And as you move towards higher energy levels or more excited states and towards ionization, it requires energy to get there. So hopefully you understand that concept, but it has to do with the electrostatic force of attraction between the electron and the positive nucleus. So remember that as an electron moves up in energy level or away from the nucleus, a photon is absorbed. It needs to absorb energy, and it does that in the methods of absorbing photons or light energy. And an electron moves down in an energy level or towards the nucleus, photons are emitted. It gives up that energy in the form of light. Generally, the electrons will lose energy very quickly and return to ground state. It requires energy to stay in those excited states, so naturally electrons fall to ground state. Again, I'm going to reiterate some of the concepts I just talked about. The emission spectra, we're looking at all of the emissions or electrons that are moving to a lower energy level. All of those electrons moving from higher energy levels to lower energy levels are going to emit light in the form of photons. And those photons, as you know, are associated with particular frequencies. So we're going to see these bright lines or these photon emissions as these colored lines against a dark background. So you'll use the spectroscope to check this out. I should have a poster up of what that looks like, the emission spectrum. You'll see a black background with brightly colored bands of light on them. And again, those are going to be different. They're going to look different for different elements. In a lab that we do, you get to see different elements and their emission spectra, and it's interesting how each one is different. Absorption spectra, we need a more technical spectroscope to observe an absorption spectra. Absorption spectra is just the opposite. It's like the negative of the emission spectrum, if you've studied photography. So absorption spectra is a bright colored background of all of the different frequencies and black lines that fall on that brightly colored background. So it's just the opposite of the emission spectra. And again, we're not going to see this with our spectroscopes. We'd need a more technical device to see it. And also, this should be on the poster as well. You can check out the absorption spectra. We know that this occurs when electrons are moving to a higher energy level, which requires the absorption of light. So I wanted to show this to you, and just in case the poster is not there. This first one that you're looking at, this first picture that you're looking at, is the absorption spectra. Emission spectra. And we have that dark background with the bright lines. And when you look into your spectroscope, this is what you should see. Now, actually, like, some of the lines are so close together that they look like just one line. So it may be that you have two emissions, but they happen very close to one another. The frequencies are nearly the same, and they end up falling in the same frequency of light, like or same color of light, and the lines end up being very close together. So it's possible that when you're looking at the overhead lights that you see multiple lines very close together, and they might look like one line. Now, the absorption spectra is this guy here. And we see the brightly colored background, and then we see where the light has been absorbed. So as a result, you end up with these black bands. Now it's time for you to do some practice on your own. So in the Prentice Hall book, if you turn to page 190, let's do 12 through 22 even, 24 through 29. You're going to transfer your answers into the questions that are going to pop up after this section of the video. Our very last topic of the entire year is called nuclear physics. And a lot of this topic has to do with your reference tables, so you want to get those out right away. We're going to be looking at the different particles that make up all of matter. And like I said, a lot of this is having to use your reference tables and see where matter is classified, how it's classified, and the subatomic particles that, when combined together, make up new matter. So we've talked about an electrostatic force between electrons and the positive nucleus. But there also exists a force between the nucleons being the neutrons and protons in the nucleus. This force of attraction between neutrons, which are neutral, and protons, which are positive, is called the nuclear force. It is also called the strong nuclear force. And it's called the strong nuclear force because it is extremely strong. And if you thought that the electrostatic force of attraction and repulsion were strong, the nuclear force is 100 times that. So you might need to pause this to take your notes. Now, energy and mass are related directly in Einstein's equation, E equals mc squared. And yes, you finally get to learn this equation. So we know that all of mass is containing all of this energy through nuclear and electrostatic forces. And when that energy is released, it's incredible. This is the process of nuclear fusion and fission, and why there's so much energy behind it. We can see a direct relationship between mass and energy. So the more mass that exists in the particle, the more energy it could possibly emit. And when this energy is emitted, it's emitted in the form of electromagnetic waves, which travel all at the speed of light, which is hence why you have the c squared, or speed of light squared, in the equation. Atoms are really, really small. And so because they're really, really small, their masses in kilograms are extremely small. And so we get these numbers with times 10 to the negative 27 and so on. And that's a huge number, not huge number, but that's a really, really small number, a large amount to deal with in your calculator. So scientists want to simplify that so that they could do more simplistic math. So to make their lives easier, they came up with something called a universal mass unit, and it's based off of 1/12 of a carbon-12 atom. 1/12 of the C12 or carbon-12 atom is 1.66 times 10 to the negative 27 kilograms. So one universal mass unit is equivalent to that amount. If we talk about the proton, the neutron, and the electron, we can divide their masses by this 1.6 times 10 to the negative 27 kilograms and see that in terms of universal mass units, we can compare the mass of a proton, neutron, and electron a little bit more easily. Protons and neutrons are thought to have the same mass, but not exactly. When you look at them in terms of universal mass units, you can see that the proton is 1.0073 universal mass units, which is 1.0073 times 1.66 times 10 to the negative 27 kilograms. That's the conversion. And a neutron is 1.0087, slightly more massive than the proton. Now, if you had this in terms of 10 to the negative 27, you would never see that small difference between the proton and the neutron. The electron, you can see, is 0.005 universal mass units, considerably smaller than the proton and the neutron. And maybe we didn't realize how much smaller the electron was until we looked at it in terms of universal mass units. Most typically, you don't have to convert between universal mass units and kilograms. It's usually given to you already in a problem. However, you do have problems that use universal mass units. So we will do an example on the next slide. Continuing on with Einstein's relationship, the mass-energy relationship, E equals mc squared, we can see that when nucleons are formed, when atoms are formed, and protons and neutrons come together to form a nucleus, some of that matter is lost. And where does it go? Well, it kind of essentially burns up and is emitted as energy. So that makes sense. Like when two objects collide together and have this fusion between them, we might lose some of the mass to energy. And that's what happens when the protons and neutrons come together to form a nucleus. So how much mass are we losing? So with this example, we have two protons and two neutrons that collide together. They form a new nucleus. Now, if we were just to add up in universal mass units, two protons, 2 times 1.0073 universal mass units, and two neutrons, 2 times 1.0087 universal mass units, when you add that all up, you get 4.032 universal mass units. However, when two protons and neutrons do collide and come together, that's not the mass afterwards. The mass is actually less. The actual mass is 4.0016 universal mass units. So it's less than what we thought it should be, which means that some of the mass is converted into energy. So the difference between these two masses is that mass that's lost, right? So we can determine how much energy that is by looking at the difference. This is the difference in energy or in mass between what it should be and what it actually was. So we have a difference of 0.0304 universal mass units. And if we want to know how much energy that's associated with, we can't quite use Einstein's equation E equals mc squared. E equals mc squared uses kilograms, and our mass here is in universal mass units. On your reference table, you'll see something called mega electron volts and universal mass unit. You'll see that conversion there. And 1 universal mass unit is equal to 931 mega electron volts. So instead of using E equals mc squared, all we have to do is use this conversion. 0.304 universal mass units. If we multiply that by 931 mega electron volts per universal mass unit, if we set up our conversion factor, it would be over 1U. And you would see that the U's cancel in that. So we multiply. You would have 28.3 mega electron volts. And when we were looking at the energy level changes in the atoms, we were seeing just, plain electron volts. Mega is times 10 to the 6. So we have a huge amount of energy being released when these two protons, just these two tiny little protons and these two tiny little neutrons are forming a nucleus. This is an enormous amount of energy. Wow, guys, you are coming to the end of your year in physics, and now we have a little bit of practice to do regarding what we just talked about with Einstein's equation, with universal mass units, with energy level changes. So check out this Prentice Hall assignment. After you're done, you're going to place your answers in the question boxes that follow this slide. All right, hopefully you did well on that assignment. So this is the very, very last slide of your entire year for notes, and we'll be talking about particle physics. So we'll need your reference tables out, and this part is all about using your reference tables. So let's first talk about some of the fundamental forces that we've talked about through the entire year. So fundamental forces, meaning what are the basic forces of the universe? And hopefully you're thinking of one being gravity. Gravity is a fundamental force that exists everywhere in our universe. Without gravity, we wouldn't stay in orbit around our sun, let alone have our sun stay in its position in the Milky Way galaxy. So gravity exists everywhere in the universe and is responsible for the movement and the binding of planets and stars in their particular orbits. The next fundamental force is electromagnetism, and we studied these two forces separately, but really they are one and the same, as you learned in the waves unit. So we have our electrostatic force and we have our magnetic force, and together they work as one, called electromagnetism. And again, this is how light travels. This is how all of the waves, all of those electromagnetic waves travel within our universe. And without electromagnetism, every single atom would split apart or collapse into a dense black hole. Then we have the nuclear force. The strong nuclear force is what is responsible for holding the nucleons together inside of the nucleus of every single atom in the universe. Without this nuclear force, protons and neutrons would not bind together. We would have no nuclear bonds to break as our sun explodes with energy as millions of nuclear explosions occur on its surface and within. The weak nuclear force we don't actually study in this course. The weak nuclear force is responsible for a lot of the decay that occurs within the nucleus of an atom as an atom changes from one element to another. And we don't study that in this course, but just know that there is something called a weak nuclear force. So these are the 4 fundamental forces of nature, and you need to know each one. Now we're going to take a look at the standard model. So open your reference table to the standard model. You should see the standard model and you should see classifications of matter. Let's start with the classifications of matter. All matter that exists in the universe can be divided into 2 groups, hadrons and leptons. Hadrons are mostly what we know of to be matter. Leptons are these kind of strange particles that the only one that we really know about is the electron. So our leptons are here in the standard model. You can see that there's an electron, which we're familiar with, something called a muon, tau, electron neutrino, muon neutrino, and tau neutrino. And some of these leptons are a little bit mysterious. However, so the electron is kind of different in a way because everything else falls into the hadron family. In the hadron family, matter can be comprised 2 different ways. There's the baryon, and with the baryon is comprised of 3 quarks. I'll tell you what a quark is in a second. The meson is comprised of a quark and an antiquark. Again, you don't know what these quarks are yet. But the point is that baryons and mesons are made up differently. They are comprised of these quarks in different ways. And so that's the difference between a baryon and a meson. Now, baryons we are very familiar with in that they make up your protons, your neutrons, and so we're familiar with protons and neutrons. So a lot of our matter is made up of baryons and leptons because we have protons, neutrons, and electrons that comprise our atom. Mesons, quarks, and antiquarks are combined together to make particles. So we're really making particles here, and I need to talk to you now about what a quark is. What are these particles that make up matter? So if you thought that you couldn't get smaller than a proton or a neutron, you are mistaken. Protons and neutrons are made up of, and other particles too, are made up of 3 quarks. These 3 quarks combine together to make either a +1, a -1, or a neutral 0 electric charge. So we know that we can't have part of a charge, which is why 3 of these quarks need to come together to make up a particle. So for instance, you can see that let me get my highlighter. You can see that the up quark, which is represented with a U, is 2/3 of an elementary charge. The charm, which is represented with a C, is plus 2/3 of an elementary charge. Top, T, again, plus 2/3 of an elementary charge. And then you have your down, D, your strange, S, and your bottom, B. All of those are -1/3 E. So you can combine three quarks together to make a +1, -1, or a neutral 0 E charge. So let's say we put an up, a charm, and a strange together. You can see you have +2/3, which is +4/3. -1/3 brings you back to a +3/3, which is a +1. So you can see how you can combine three quarks to make a +1 or a positive charge. You can do the same thing with a negative charge. So let's say we want to make it, an easiest way to make a negative is we take a down and a strange and a bottom. And so we have -1/3. And let's say that we want to make a neutral. Neutral we could make by combining, say, a top and a strange and a bottom. Here we have +2/3, -1/3, -1/3 brings us back to 0E, which is neutral. One of the things that you do need to memorize is that protons and neutrons are made up of just your up and down quarks. So just ups and downs. So let's figure out if you can make a proton using up and down quarks. Remember that the proton has a +1E, one elementary charge. So can you try to combine up and down by combining three quarks to make a positive charge? Can you now combine the ups and downs, three total, to combine to make a neutron, which is a 0E charge? So please remember that neutrons and protons are made up of up and down quarks in combination. Now I'm going to ask you a series of questions. I want you to be able to use the standard model, combine three quarks together to create a positive, a negative, and a neutral charge. Remember that when we combine three quarks together, we are looking at the baryon family. So right now I'm going to ask you to make up those baryons, okay, which are comprised of three quarks. Now we're going to make mesons. Mesons are comprised of a quark and an antiquark. So what the heck is an antiquark? Well, if we look at the quarks, an antiquark is just the negative of the quark. So there's a little bit more to it than that, but to keep things simple, if we look at the up, an anti-up would have a bar on top to signify that it's an anti-up. So there would be a little bar over top of the U, and the sign of the charge would change to a negative. So we're basically negating the charge, and we are putting a line on top of the symbol. So an anti-charm would have a bar on top of the C, and it would be -2/3. Anti-top would have a bar on top, and then -2/3. Anti-down, bar on top, and it would be +1/3. Anti-strange, +1/3, and anti-bottom, +1/3. So we can combine two quarks, an antiquark and a regular quark, to combine to make those three charges of +1, -1, and neutral, 0. So if we take, let's see. So if we take, let's see, let me get rid of some of these lines here. If we take a top, anti-top, which is -2/3, and a strange, because we want to combine an antiquark and a regular quark. So we have -2/3 for the anti-top, and then we have another -1/3 for the strange, so that gives us a -1E when we combine the two. Let's try another one. So we need a quark and an antiquark. So let's say we take an anti-down, which is plus 1/3, and we take a charm. Let's get rid of, whoopsies. Let's get rid of the, oh, I can't. Let's just make that a positive again. So let's take a charm and the anti-down. That's another plus 2/3. So with the anti-down of plus 1/3 and the positive 2/3 of the regular charm, we end up with a positive 1. Let's see if we can make a neutral. So if we take a strange again, and we take our anti-bottom, we have a negative 1/3 and a positive 1/3, which ends up being neutral. That's a 0E. So you're adding the charge together to make a +1, -1, or 0 electric charge. And that's really important. You can't have part of an electric charge, except in these quarks, but they only combine together to make +1, -1, and 0E. So if they don't add up to +1, -1, or 0E, it's not a possible charge that could be found on a particle. It's not a possible particle. So I hope now that you can see how we can make up baryons, which are comprised of 3 quarks, and we can make mesons, which are comprised of a quark and an antiquark. And all of those particles, when they are combined, do need to add up to +1, -1, or 0 electric charge. So this is how we use our standard model, and we classify matter in different ways based on how those particles are combined. So let's try some practice. In your Prentice Hall book, you'll complete the questions assigned here, and you'll put your answers in the questions that follow this slide. So guys, this concludes your final lesson in Regents Physics. And I hope that you've learned a lot in this lesson. I hope that you're able to complete these problems, and I wish you all the best of luck in your review. Please take your review very seriously, as you will be graded on a lot of your review questions. I want you all to do very well, so that will take some studying and some hard work on your part, and I'll be talking to you soon.